Okay, in this presentation, we are going to show an approach to model residential electric energy consumption at the urban scale using common census information, free access prototype building energy models, and aggregated electricity utility data. So our approach can be classified into the urban building energy models, UBIM, that refers to the simulation of energy use of multiple buildings across different urban contexts at different urban scales. These kind of models can be divided into physics-based and data-driven approaches, but currently there is a necessity to combine these two different approaches to achieve better accuracy and scalability in these models, and most importantly, to capture, integrate interactions between different factors that affect energy consumption. So within that, statistical and data mining techniques can be really useful for this kind of models, especially to unveil hidden patterns within complex data, identify influential variables for precise modeling, enhance accuracy through data optimization, and ensure model robustness and real-world applicability. Considering this, our research objective is to develop a data-driven methodology for identifying and categorizing building energy models archetypes by using household and demographic information at the census-tract level to model monthly residential energy use. So the data we have, we have US Census data. We have 31 continuous variables that we classified as demographic variables, building information variables, land cover percentages, racial percentages, and household variables. We also obtained monthly electric residential energy use for the months of May, June, July from year 2019. We obtained this data from the Salbury project, which is the utility company for the metropolitan area of Phoenix. And we obtained data for 429 census tracts that correspond to nearly 48% of the whole metropolitan area. We also use single family detached house prototypes, building energy models house prototypes that were developed by the Pacific Northwest National Laboratory and the U.S. Department of Energy. So the approach we are proposing is a step-by-step approach. So the first step is to focus on data preparation, but we focus in detection of multicollinearity. After that, we made a variable selection procedure. Then we did a cluster analysis. With that clusters, we identified social homogeneous areas. With that, we adapted the building energy models archetypes to this context. With the simulation we obtained from those models, we interpolate and extrapolate for the whole metropolitan area at the census tract level, and then we validate with our utility data. So the main statistical techniques we use for detect multicollinearity, we employ the variance inflation factor, which is a value by which the variance of a predictor is inflated by the existence of correlation among the predictor variables in the model. So a value greater than 10 means that there is a high multicollinearity. So we also perform automatic selection technique that is called backward step progressions that consists in remove variables iteratively until the mean square error is minimized. And the purpose of this is because we wanted to improve interpretability of the variables and enhance the predictive power of the predictors. For the cluster analysis, we use k-means clustering, that is a method for data partitioning that is based in the formation of centroid-based clusters. We minimize the variance within clusters, and we use the Euclidean distance as measure of the similarity. So to test these clusters, we decided to perform stability validation. For this, we performed some variations in the original datasets by doing bootstrap, that is a technique for sampling and subsetting. In this case, we remove some observations, and we duplicate some observations, and we perform the K-means clustering. We compare both clusterings to see if the observations are classified in the same clusters. So we measure that similarity by using the Jaccard coefficients, and that gave us an index that goes from 0 to 1, and the closer to 1, the more similar the two clusters are. We also perform a visual inspection to test compactness and separation by using box plots and GIS mapping, and this also helps us to identify the social homogeneous areas. For the building energy models, we use the single family detached house prototypes, as I told you before, for a small house and a large house. We obtain typical weather information for the metropolitan area of Phoenix for the year 2019, and we use Energy Plus as our main engine models. And we validate the whole approach by quantifying the coefficient of determination and the root mean square error. So as a result for the various inflation analysis, we identified that there is a high correlation when we use all the variables. So some variables such as the percentage of population that have a bachelor degree and the price of house and the price of or rent are highly correlated with household median income. So we decide to remove those variables and we reduce the multicollinearity. After that, we perform backward state regression and we obtain a model with 12 variables. To test these variables, we perform lead one out cross validations, and we obtain an in-sample and out-of-sample coefficient of determination on 0.93. So these are the main variables that were selected according to the different type of variables. And the main point that we want to highlight here is that household variables can explain the variation in energy consumption by 84%. And we also calculate the partial coefficient of determinations relative to these household variables. And we found that if we decide to add building information variables, we can increase the prediction power by 40%. If we do the same with land cover variables, we can increase by 25%. And with demographic variables, we can increase the model predictivity by 13%. If we add some rational variables, we don't have a significant increase, despite these variables are significant for the selected model. Another important relationship is that we decide to split the dataset according to the household income. So we have a dataset that group low-income households and another for high-income households. We found a strong linear relationship between the number of rooms and residential energy consumption. So we use this variable, the number of rooms, as an interpolation factor. Here are the results for the K-means clusterings. We found that the clusters that begin with 3 to 7 clusters minimize the most the variance within clusters for both datasets. When we perform the stability validation, we found that most of the number of clusters are closer to 1. But if you see the numbers that are related and that are next to each dot, and each dot represents each cluster, is the number of times in which that cluster wasn't the same during the bootstrapping sampling. So that is not the case for the clusters when we use 3 clusters for both datasets, that most of the cases was always the same cluster. So we decided to use 3 clusters and we assess a visual inspection. And as can you see, there is a clearly partition between the data. Importantly, when we analyze the annual home age, so we decided to divide these datasets in very old homes, and recent homes. So with that information, we can propose some social homogeneous areas for very old homes and with high income and low income, old homes with high income and low income, and recent homes with high and low income. With the other variables, we can analyze that information to create a description and to contextualize the social context of each cluster. With, a, with the Energy Plus prototypes, we also use that information to adapt those models to our context. But we also decided to add more variation to the simulation by changing the rotation of the building and the schedules uh, of the models. We aggregate that data to obtain individual values for each social homogeneous areas and for two different number of rooms. And we interpolate that information to the whole metropolitan area. Here is the validation of that interpolation extrapolations. We found that our approach is able to explain more than 50% of variation in residential energy use for all the social areas. There are some big errors in the very old social areas that suggest that we need to improve the calibration of the building energy models. When we validate for the whole metropolitan area, we can see that our approach mimic pretty well the distribution of residential energy use, but we have overestimation. So that can be related to the need of a better calibration procedure, but also to another uncertainties in terms of occupancy behavior. So to finish, we found that household and building-related factors play a vital role in explaining the variations in total residential energy consumption. We show that using common census data, available building prototypes, and by obtaining aggregated energy utility, we can feed a UBN model, a reliable UBN model. And for the future, we need to conduct more research about how to better calibrate these models and also how to better represent microclimate and occupant behaviors variations in this approach. And we also need to test this approach to assess energy use efficient strategies and future climate scenarios. So thank you.